Okay, I think we're going to get started. Wanted to welcome everyone. Thank you very much for joining us today for the live demo. My name is Eric Fitzpatrick, the Director of Solutions Engineering here at TidalScale. Also presenting with me today will be my colleague Gurinder Brar, and we're going to be showing you how to increase Oracle database performance while driving down the operating costs associated with that database. We have a lot of database administrators that are joining us today, so I think you're going to see something here that you haven't seen before. At least very few. In the next half hour, we're going to show you how you can build a software-defined server of any size in just a couple of clicks. You will see a brand new virtual system boot up in just a few minutes, and then you'll see the impact that that has on your live Oracle database performance. So we'll be doing both a demo of the TidalScale software as well as looking into the Oracle systems that are running within a traditional and TidalScale system. Before we start, a couple of quick housekeeping notes. This webinar is going to run about 30 minutes with a 10 minutes of Q&A at the end. So you can just, to submit a question, tap the Q&A button. It's located at the bottom of your screen. And you can just type in your question there and we'll answer that. If we don't get to your question at the end, we still would love to speak to you one-on-one. Feel free to reach out to us. We will share our contact info at the end, as well as a way of contacting us for more information. And if you had anyone who couldn't join us, please, we'll be sharing a recording of the webinar after this, so please be on the lookout for that. It's a good way to see something again that you may have missed, or if we went too quickly, or to share with video with colleagues or loved ones who just want to see how it works. So, without any more further ado, what is a software-defined server? So to begin understanding a software-defined server, we're going to root ourselves in what traditional virtualization is. By now, most of us are very familiar with traditional, VMware, the grandfather of VMware. It allows you to create many small virtual machines on one physical machine. So do it very quickly. You don't need to make any changes to your operating system. You just install your standard, whatever flavor of Linux you want. You just go ahead and install that. And the entire purpose is to get more out of a single server. So that's VMware. That's traditional virtualization. Software-defined servers. So TidalScale, what we do is we like to say it's the opposite. Instead of taking a single system and breaking it up into multiple smaller virtual machines, we take multiple physical systems and we combine those into a single larger virtual machine. So from many comes one. Again, very similar to traditional VMware, traditional virtualization. No changes to the OS. Take your, whatever Linux system that you love, go ahead and use that without any kernel changes, no special drivers. And again, this is done in just minutes. And we're going to start off in a few minutes, and we'll kick off a live demonstration of this. The nice part about this is it's all done in software. So if I want to have a 2-server system, a 3-server, 4-server, 5, I can just keep on changing that in minutes. And the purpose here is not to increase the utilization of the server. It's to actually have more data utilized, not having to have data sit on disk or not be utilized or not addressable. So we've been around for about 5 or 6 years. So we've got a nice stable of partners and customers. Basically what we're looking at here are people who have a very large workload and needed to size the server to fit the workload. So let's talk about some of the things that TidalScale and software-defined servers bring to the table. So the number one is in-memory performance. That is the number one thing that we do, is provide an extremely large amount of contiguously addressable RAM. And underneath, we have a machine learning system that I'll go through in a few slides while the systems boot. And so this allows us to have incredibly fast performance. Flexibility is the second one. So one of the things I like to say is that we're somewhat getting the best of both worlds of scale up and scale out. For scale up, we get really the simplicity, and for scale out, we get the size. So if I look at the flexibility, I get massively scalable. I can just keep on growing depending on if I'm using a 1.5, 3, 6, no matter how large of an individual node, I can keep scaling those and growing those as I need it. So what's really nice there is if I'm going to grow 20% a year, year over year, I don't need to buy something for 4 to 5 years down the line. I can purchase what I want today and build as I grow. And if that 20% growth rate turns into 10, or if it turns into 30, I can react to that with a lot less waste or risk of accidentally outgrowing my system, which is the absolute worst. Cloud or on-prem. So we're available in various cloud providers, and we're also available, of course, on-prem with your own equipment. The easy part, this is the part where I say it's the scale up portion that we give you the best of. It's extremely easy. You'll see it's just a couple of clicks, and we're running. There's no data sharding. I don't need to take a 7 or 8 or 12 or 24 terabyte workload, no matter how much your data, how big your data set is. You don't need to sit beforehand for years trying to decide, do I go by fiscal period? Do I go by year? And it's very easy to manage. So, if you've run a simple virtualization program in the last 10 years, this will come right along the same lines. The other big breakthrough here is that we're not doing anything proprietary. And I always come back to VMware, and we have great respect for them. But the thing is we're not using any technologies that aren't already being used in your current data center. So everything that's already been sitting in your rack is probably all you need to run TidalScale. And similarly, I'm just going to bring this up, is we are the software provider. We don't sell a custom appliance or custom networking. We're looking at just the software component of that. So we run on x86 servers. So anything that has a V3 chip or higher, which is pretty much anything in the last 5 years. And then we use standard Ethernet. So we use 10 gig or higher. So some people do 25, 40, whatever you require, or whatever you have on premise. And we can use that to connect the systems together. So no NumaLink or InfiniBand. Again, we're Red Hat and SUSE certified. So whatever your current Linux flavor of choice, you can keep using that. And because we're not modifying the application, the operating system, we don't need to modify the application. So as I always say, it's always nice to have people tell you you can fly, but it's another thing to jump out of the plane. So this is what I'm going to show you here in a moment is our WaveRunner orchestration software. Again, going back to what we know, this is very similar to vCenter. It's your command and control, but allows you to configure, deploy, and manage your systems that you have. We also do have a GUI as well. I'm sorry, an API as well as a command line, and I'll show you the command line as well here. So first things first, this is our WaveRunner. This is an actual live system in our California data centers, and this basically says that I have 20 nodes available. I have 2 that are free, and if I wanted to put everything together right now, I could create over 13, almost 14 terabytes of RAM, a single system. So right now I have 2 free. You can see it up here on the right. I'm going to press this button and say add pod. I'm going to give the pod a name and just something fairly simple. I'll say 01 so it comes to the top, and demo. And I'll just say this is a demo for webinar. Now what's important is I come down here and I say 12 cores, 768 gigs of RAM. What if I'm going to run a 1 or greater than a terabyte of RAM for my data set? So my server currently is not large enough to fit my data set. All I need to do is come up here. I knew I had 2 free, so I'm just going to drag this on over, and I'll use both of them. And I now have twice the number of cores and twice the amount of RAM. That's perfect. That'll fit my workload. I'm going to go over here, and you notice that CentOS was chosen. For today's workload, I'm going to install SUSE. So I'll grab the latest version of SUSE Linux, and I'll tell the system I'm installing SUSE. Now I can go ahead and I can do an ISO and do the install here, but we don't really have time for that on our webinar. So what I'm going to do is I'm going to go down here and grab a template. Once I install a system and configure it for whatever application, I do all my specific tunings. I can take that and make that a template and just deploy that over and over. I'm happy with everything else. I'll leave everything as a default. I'm going to just hit OK. Right now, we're going to build, quote unquote, build our virtual server. And all that's doing is it's just copying files to create the systems in the back end. So here is my demo system. I look and I can see I've got my 2 nodes in there. Now, first thing I'm going to do is I'm going to power them on. Power on the pod. What'll happen is I'll send a command to the 2 servers. They'll turn on, and they're going to boot what we call our hyperkernel. Now, our hyperkernel is very similar to the a standard hypervisor, except it spans across both systems. So we'll actually run 2 instances of the hyperkernel on 2 separate systems. And then in the next step, they'll communicate to run the guest. So we could sit here for a couple of minutes and watch the lights blink, but that gets a little boring. So I'm going to show you underneath the hood what's going on. So I'm logged into my WaveRunner. This is the command line. All of my commands are going to start with a WR, and I'm going to say pod.node consoles. Oops, I have to tell it to, I'm going to use the 01 underscore demo. And now I'm going to say pod node consoles. Now, what I'm going to see here is the screen is split in half because I have 2 systems. You should say if you have 4, 8, up to, so it'll just keep splitting the screen up. And what's going to happen here is right now, we're pixie booting those 6 systems. So we're taking our hypervisor, a copy of it is being copied from the WaveRunner system onto these nodes, and they're going to start booting up. While that's going on, and while those are happening, I'm going to go back to the presentation and show you a little bit more of what's happening. You know, what are we doing? What's the magic to see what's going on the servers? So I'm going to just close this down for a second. This as well. And so what we have going on now, if I look at what's happening, I have 4, in this slide, I have 4 bare metal servers. So they're sitting in a rack in California. And these are multiple separate physical servers. Now what TidalScale does is we take all of those resources and we're going to combine those into you can see it's nice glowing, a single TidalScale virtual software-defined server. So that's the 2 layers that we've put together. Now, what's important to realize is that all of the resources that are on the underlying physical systems are now addressable by the single integrated TidalScale software-defined server. So many people always ask, well, how are you going to do that if you've got a CPU on one system and you've got RAM on the other system? There's obviously an air gap there. How are you going to connect those 2 together? And again, we have our entire system is hooked up in the back end with standard Ethernet, so minimum of 10 gig Ethernet. What we're going to do in this instance, I have a virtual CPU that is connecting to this RAM. Now, this is completely fine and acceptable at a higher level. Underneath, we're having a little issue here as far as there's a separation of the 2. So what's going to happen is the machine learning notices that there's an issue, and our machine learning is included in our inverse hypervisor. So it makes the determination that the best thing to do is to copy that RAM page over the network. But it also learns that CPU and that RAM have a relationship. So it starts working on what we call creating working sets. And these working sets show that there's a relationship between those pages of RAM to the CPU. Oftentimes, if I'm searching through a table or a column or a partition, I'm going to start pulling all those pages of RAM together in the same time in the correct order, and the machine learning is going to start watching that. And what will happen is you'll start getting working sets across the systems of RAM that wants to be together and threads that want to be together. So I moved that because it was maybe just a few pages of RAM. But what happens if I have a virtual CPU that needs access to a set of RAM, a page of RAM, and it's not just 1 or 2 or 4 pages of RAM, but it's part of a much larger working set. It could be 100 gigabytes. Obviously, it'd be extraordinarily inefficient to move it all over here. I'd have to make room on the server first, the first one, and then I'd have to move from the second. So I might have to move 100 gig from 1 to 3 and 2 to 1. And that's just going to take too long. It's highly inefficient. And we all see there's a better solution. Of course, the machine learning does as well. It decides, well, it's a lot easier for me to take this virtual CPU, 1 machine cycle, I stop my execution, put the entire thread context in a jumbo frame over that 10 gig network, and I place it on server 2. What that looks like is it looks like a virtual to physical address translation that was missing and it needed to swap it in. So it looks like terabytes of swap just occurred, and it takes 1 machine cycle for that CPU to continue. So again, it's a machine cycle to stop, 1 jumbo frame to migrate, and another machine cycle to start. So that's what I call the magic underneath of what's occurring. I'm going to go back real quick, see how so now our hyperkernel, I can see my hyperkernel is up and running on both of these. So if I come back and I look at my GUI, so we're going to go into the GUI, I can see that things have stopped flashing, everything's green. Now what I want to do is I want to actually start my guest. Now I could have done this with a WR space guest.start at the command line, but GUI is a little nicer. So one of the things that's going to happen now is previously, before executing the guest, these two hyperkernels were both running an independent version of the hypervisor. They really didn't have anything to talk about, so they weren't using the interconnect. The first thing that happens is that both of these announce themselves and find their partner, or in the case of a 4, 16, or 20 or higher node system, they all make sure that everyone is available and in the proper state before starting the guest. Now, again, I could sit here and just watch the lights, but I prefer to sit here on the guest console, and you can see I'm booting SLES 12 SP3. Got a lot of RAM, so it's going to load a RAM disk. So again, what I'm going to do here is I'm going to jump ahead, and I'm going to take a look at some of the other, what are we going to do now that we have a system? What are we going to do with it? And let me close that so I can minimize. So, specifically talking around Oracle, now that I have a software-defined server, what am I going to do for Oracle and my Oracle operation costs? Right off the bat, one of the things you can see here, if I look at a traditional scale-up system in red versus a software-defined server in blue, the first thing you notice is that in year 1, I don't need to go ahead and buy everything I need for year 4. I don't need to buy all my hardware. I don't need to try to use a crystal ball to try to guess what that hardware is. And I also don't need to buy all the licensing associated with that. So basically, I'm allowed to reduce my TCO by buying what I need when I need it. And the other thing is that the licensing, not the licensing, sorry, the hardware at least, hardware costs actually do go down over time. So let's go back real quick, and we're going to look at our guest. And now that my guest is up and running, so if I can look at the console, I can log in. And I can actually see that I have a fully operational system. All the RAM I need, standard disks, and everything. So now that I have the system, let's look at what we do when we have a benchmark running on that system. So I'm going to take a system, and Gurinder is going to show in a moment. We have 2 systems available. On the left, we have here this is a traditional system, 28 cores with 768 gigs of RAM. Now, in this case, what we're looking at is a system that has outgrown, its footprint. So this system is actually now too small. My option is normally to take this system, throw it away, go buy another one, and then, basically double my costs, or basically I have one system here and get another one that's larger. My option with TidalScale is to take 2 systems using a smaller amount of cores per system, but with larger RAM. So I can address more RAM actually with less cores. So that's the setup of what we're going to show you here now is 2 separate systems running a traditional bare metal small server and a TidalScale software-defined server that can scale. So Gurinder, if you want to go ahead and take the helm, you can show everybody.
Thanks, Eric. I hope everybody can hear me.
Yep.
So here what I have is a single bare metal system with 768 gig of RAM and 28 cores, as Eric had put in this previous slide. What I'm going to do is make it a little bigger so we can see it. In the system, I had given about 510 gigabytes to SGA. That's about maximum I could give because I had to give out another 20% to PGA and leave 10% for Linux. My data set is about 600 gigabytes. And what we're running is a star schema benchmark. And the scale factor equals 1500, and I have 9 billion rows. From this screen, you can see the queries are running with a degree of parallelism of 56, and this is a 13 query set that I started running. Making the screen go a little wider, you can see all the CPUs are being utilized where most of that is going towards user I/O, very little really for user processing. And if I were to look at how the queries are progressing in this one, again, now let me make it a little bigger so that not cooperating, so I'll go back. You can see my last set that just finished a few minutes ago, completed in, here we go, is 7,100 seconds. The one before, another 7,000 seconds, one before 7,000 seconds, one before 7,200. So system is in a steady state. It's taking about 2 hours to complete this query set. And if I were to look at what is happening, and at this point in time, the information that was given to us by customer was their data set had grown from 6 billion rows to 9 billion rows, and time went from about 25 minutes to almost 2 hours. We ran a AWI report and basically is saying is, hey, very clearly, you have undersized SGA. And there's, of course, other recommendations that come from Oracle. So based on this information, what we decided is what we're going to do is make a software-defined server with 2 nodes and double the memory. And by doubling the memory, I wanted to be fair that this server had 28 cores. What I wanted to make sure that we go with, okay, let me, a server that had fewer cores. So this one, I have 2 systems, dual socket, each socket with 6 cores, so a total of 24 cores. What I did is was checking, and I gave a degree of parallelism equals 20. We didn't use hyper-threading because in my experience, I found out that Oracle actually likes cores with more gigahertz rather than small threads. Same data set. Because I have 1.5 terabyte of memory, I was able to go to about 900 gigabytes, 950 gigabytes for SGA, out of which 650 was for in-memory and about 150 gigabytes for PGA. And from this screen, as you can see, that everything is running in memory, and system is not oversubscribed. Like last time was completely pegged. This one is, I would say, about 50% utilized. Actually, I should have done is reduce the core down to even 16, because that would reduce Oracle costs a lot lower, and system would run about 80%. Other benefit with this one is if data set grew suddenly again, you just add the 3rd node. Whereas on the other, if you were to go with a larger footprint system, bare metal, if data set grew, then you have to throw that system away and replace it again. So this becomes a very, very nice, and to give you an example how my queries are running, basically you can see I have now completed about 30 sets, and each set is completing in about 300 seconds, 5 minutes, just doubling the hardware. And by reducing the number of cores required for the system for Oracle, I've been able to gain about 20x, from 7,000 to 300 seconds in query completion for the whole set. With that, I'll turn it over back to you, Eric.
Thank you very much, Gurinder. So just to summarize what we saw here, if I look at it as a bare metal as my baseline performance, when I take that over and I look at what I was getting by moving to a TidalScale system, again, less cores, more memory, better performance. So I'm looking at about 20 times my performance. And because I have less cores.
Can you share your screens, please?
Oh, sorry, there was an extra button. There we go. Thank you. So if I take the bare metal server as my benchmark, when I move over to the TidalScale system, I'm actually getting 20 times the performance. And because I'm saving so much money on Oracle licensing, it's actually, and hardware, 22x the queries per dollar. So just to wrap up, that's exactly how you can use a software-defined server to get more value out of your existing implementation or any other new greenfield implementation.